in common. So let us discuss now common emitter configuration. So common emitter configuration is now. See, I'm already now I will.
Sir, your voice is not clear,
Yes.
sir.
Yes.
बहुत कम है आवाज.
आवाज कम है. Okay. Is it okay now? Okay.
Yes, sir.
So this is now NPN transistor. Okay. Let us say this is emitter, this is your collector, and this is your base. Okay. Now common emitter means now this will be your grounded. This will become ground. Okay. Now you will apply voltage here, and your voltage will be, I'm calling it a VB this time because it's connected to base. So this is a VB. Okay. And similarly, and here I am applying, so NPN, I'm applying forward bias. Okay, P is connected to plus, and this is my N. So again, I am applying this with a source called C. So I'm calling it VCC, and this is also variable. Okay. Now suppose if I am applying VBB, what will happen? I require a voltage drop VB here. Okay. So understand clearly what I'm doing here. I'm applying the voltage between these two terminals is VBE. VBE. Okay. Now, when I apply VBE, what will happen? My forward bias current will flow. Okay. So I was discussing with you the input characteristics. So input characteristics is basically the graph between input and input current and input voltage. Okay. Now here the input current is your IB. So IB current is flowing here. So if I plot the graph IB versus VB, what happened? Okay, initially you require 0.7 volts. Okay, and then it will feel almost it will fixed, and you apply if you increase the voltage. Okay, and this you will get current like this. Okay, now here I'm keeping the voltage fixed. If I keep the voltage fixed, automatically the voltage across this terminal, which is called VCE, that is fixed. So keeping VCE fixed, I am varying the VBB. I'm varying the VBB, okay, and keeping the VCC fixed. Is fixed. This is the collector. It's collecting whatever you're applying current here. So this graph is called input characteristics, and this is your VBE is almost around 0.7, and say VCB is now 2 volt. Okay. VCB means VCB is voltage between this one. This is called VCB. Or here I'm applying, sorry, VCE. This is my VCE. Output voltage is now VCE. Okay. Output voltage is VCE now. And this is the input voltage, input current. So keeping VCE 2 volt. Okay. Now VCE also, once I increase the VCE, that means automatically I'm increasing VCB. Okay. Because VCE is VCB plus VBE. Now this is almost fixed. This is almost fixed. That means whenever I increase the VCE, I increase the battery, and battery will increase, the VC will increase here. When VC increases, automatically VC is equal to VCB plus VBE, your VCB will increase. Okay, that means the reverse bias. Okay, you don't see this junction. Junction is these two. Okay, this one, and this one. There's two junction, collector base and your this one, emitter base. So your collector base junction should be reverse bias for the normal operation. If you want an active region amplifier, okay. So automatically I am applying plus here. So this is plus, this is minus, this is plus, this is minus. So this is a plus, this is a minus, already ground. This will be plus, and this voltage, full voltage is equal to this volts, and you're applying this volts. Okay. So now suppose if I increase the VCE, okay, suppose increase the VCE equals to 4 volt or 3 volt. So when I increase the VCE equal to 3 volt, automatically my VCB increase. My VCB increase means my reverse bias increase, And when my reverse bias increases, the depletion layer width, this depletion layer width will increase. Okay, and depletion layer width increase means your IB goes down because the base thickness decreases. Okay, so I'm writing here VC increase the VCE increases VCB. Okay, when VCB increases, okay, the collector base junction width, I call it VCB, width, collector base junction width increases. Collector base width, depletion layer width. Okay, so let me call it depletion layer. Okay, so say V depletion, okay, at collector base junction increases. Okay, when width increases, automatically what become the base layer, base thickness. Okay, thickness of base become thinner, base becomes thinner, and when base becomes thinner, automatically your IB decrease. Okay, now if I want to apply, I want to get same IB which I was getting here, or I was getting here, whatever IB I'm getting here. If I want to get same IB, I need to increase little bit my VBE. Okay, so if I get the same current, now my VB will slightly change. It's almost 0.7, but very slightly will change in millivolts. Okay, so I call it, like, call this voltage as a 0.7 volts. Okay, whatever the VC is there, slight change will be in VB, but your VB will fix. So this is your, now if I say, if I take VC equals to 5 volt, again the depletion reverse bias increases, VCB increases, and you need, if you want same current, you need to increase slightly the what is VB. Okay, so that you understand. So there is very less influence on VB increasing your VCB or VCE. Okay, this is your input characteristics. Okay, now let us discuss the output characteristics. Is there any doubt in this input characteristics? Okay, so if you don't, no doubt, let us discuss the output characteristics. So output characteristics, what will happen? Output characteristics basically the current relation, a plot between output current, that is IC, okay, and versus output voltage, which is we have VCE. Okay, and keeping the IB constant. So I will apply some IB, or suppose in the beginning this VBB is 0. If VBB is 0, this VB is also 0. That means this is reverse bias. Okay, so no current will flow. If I'm not applying any VBB, there will be no drop. No drop is no current. We can assume that this junction is reverse bias. Okay, so in the beginning, when IB this is 0, IB 0. So IB 0, and I'm increasing this VCE. So when I increase the VCE, at least there will be reverse bias current, but which is called reverse saturation current flow. So I'll get very small current. Okay, and I'm keeping IB 0 here. I'm keeping IB 0 microampere. Okay, and so this current IC, yesterday I discussed, this is your reverse saturation current. At this time you can call it ICEO. Okay, reverse saturation current in common emitter configuration. Now suppose I will increase the battery slightly, so my VB will become 0.7. Okay, and I get some current. Okay, and some current, say now this current is say 100 microampere. And if the current gain for the given junction, given NPN transistor is, say, let us say 100. Okay, that is IC upon IB. So this is 100. So when IB is 100 microampere or 10 microampere, what should I 10 microampere? And if I do this 100, this took IC will become automatically 1000 microampere. 1000 microampere means it will be 1 milliampere. Similarly, if I slightly increase the IB by changing the VBE, okay, or battery VBB, okay, what will happen? So you see, if I increase this voltage VBB, my VB doesn't change much, but current changes. The graph you have seen input curve. If you're increasing this VB battery, the diode, okay, there will be no change in the drop here. See, this drop is almost same, but current is keep on increasing. So this VB, let us this be always fixed 0.7. Okay, with slight change in millivolts. Okay, but current changes. So I'm changing the current now. So say let us current is now IB is 20 microampere. It is all our IB values. Okay, so say IB is 20 microampere. So beta is 100. So automatically in the circuit I'll get current equals to 2 milliampere. Okay, similarly you keep on increasing IB 30 microampere and you get IC equals to 3 milliampere. IB is equals to 40 microampere. IB value is very less. Okay, you have to see IB is always in microampere, and then you get here 4 milliampere. Okay. Now this region, below this region, when IB is 0, you are forward. You are this region में क्या है? You are forward. This EB junction is also forward. EB junction is reverse bias. Reverse bias. Okay, and obviously when VC positive, the VCB is also positive. The VCB positive means this is also your CB junction. Okay, in this region I'm talking, your CB junction is also reverse bias. So both reverse bias, then the operation region is what? Operation region is what? When both reverse bias?
Cut off.
Cut off. Okay, so that region is called cut off region. So this region is called your cut off region. Okay, and now you're increasing IB. That means now this region, in this region, this is called active region. Active region, why? Because your input junction, EB junction is forward bias. EB junction is forward bias, and CB junction is reverse bias. Reverse bias. So this area is your active region. Okay, and very close to 0. Okay, very close to 0. What happens if VC is 0? Okay, then VCB will be positive or negative? Tell me. If VC is close to 0, okay, then VCB will be always negative because this is a plus 0.7. Okay, automatically VCB become negative. When VCB become negative, this junction also becomes forward bias. So this region, okay, close to 0, this region is called your saturation region. Okay, this region is called your saturation region. Because now your VCB 0, that VCB becomes automatically negative. Okay, because this value is VB is your 0.7. Okay, so your VC actually should be greater than 0.7 to make this junction reverse bias. Okay, so but we call it, suppose silicon is that, and we should be at least 0.3 to make it to make it 0. Okay, so anything greater than 0.3 for germanium make this junction reverse bias. Anything greater than 0.7 will make this junction your that is reverse bias. Okay, so that you have to remember that thing. What is the VC value? Okay, so VC should not be 0, or VC should not be close to 0. Okay, that is the working of your common emitter configuration. Okay, so now let us do some problem, then your clarity will increase. Okay, that what I'm trying to say. So I'm dubbing this one.
Yes, sir.
Now let us say that I have a transistor. Okay, and this transistor has a value called 200 ohm. Okay, and this is your plus, this is minus. Okay, this is called 5 volt. This is the VBB. Okay, this is your transistor. Here you have a VB 0.7. Okay, and here you have a collector. Okay, plus minus, and this is your 3 kilo ohm. Okay, this is your 3 kilo ohm. Now I want to find beta for this transistor is given 100. Okay. Now I want to find the operation region of this transistor. I have already given the biasing, and this is your 10 volt, and this is 5 volt. Okay. Now you're asking the question. Okay, what is the region of operation? Okay. So let us find and find the operating point. So find the operation region and operating point. Okay. Now what is operating point that I'm discussing here? Operating point. Okay. So first of all, let us calculate what is the value of VCE. Obviously, VCE, this is 10 volts given. So VCE, okay. So VCE and IC is called your operating point. So this is a collector, okay, and this is an NPN transistor. So NPN current will go always away, okay. And this is the emitter is common. So this is your emitter, okay. This is your collector, C, okay, and this is your base. So from base always a current flow IB, okay. Emitter say and current will come from your IC. Whatever current goes in the collector, that is called collector current. Okay, whatever current comes out of emitter, that is called emitter current. This is your emitter current. Okay. Now let us first find what is the value of IB in a circuit. Okay. So this is my input loop. Okay, this is my input loop. This is my output loop. So I'll apply KVL here. So this will be minus 5 volt plus IB RB. Okay. So IB into this value is given 200 ohm. Okay, let me check 200 or 2 kilo, 200 kilo ohm. Let me check this one. So 200 ohm. Okay. Now this is 200 ohm, and the drop here is VB, that is 0.7 volts. Okay. Tell me what is the value of IB. So IB will be 5 minus 0.7.
0.0215.
0.0215. What, milliampere or microampere?
Milliampere.
Okay. 0.0. So you're saying this is 0.0215 milliampere. Okay. Am I correct? Okay. If you solve this one, so this should come. Now this is milliampere. Okay. Now beta is given in the question. So beta is given 100. So your IC will be automatically beta IB. Okay. And it is 100 into this one 0.0215 milliampere. Okay. And if I solve this one, this will give you 215 milliampere. So you now you have the IC value also. Now let us find what is your VCB, because in order to find whether it is reverse bias and forward bias, you need either VCE value or VCB value. Both are same, okay? But those will still give you same information. Now you have IC equals to 2.15 milliampere. Okay. So I'm rubbing this one. Okay. Now अब इस loop में आ जाओ. इस loop में क्या होगा? You have a VCC. This loop I'm going like this. I'm starting from minus, so minus 10. Then I'm coming here, so this will be plus drop IC, okay, into 3 kilo ohm.
Sir,
Yes, tell me.
sir, 200 is in ohm, now then why milliamp?
That you should get. That's why I was asking. Divide and tell me the answer. What are you getting? 4.3. 4.3.
4.3 by 200 equals to 0.0215 ampere.
You're getting ampere, na? Okay, that's why I'm
Yes.
asking. Okay, then make it kilo ohm. Just make it kilo ohm.
So,
Ah,
0. It was 2.15 divided by
सर आवाज
100.
नहीं आ रही इधर.
किसकी आवाज नहीं आ रही है? हाँ, बोलिए. हाँ, अब कैलकुलेशन
4.3 divided by 200. It was 0.21 milliampere, ना?
वही मैं पूछ रहा हूँ कि मिलियन पे तुम्हारा आंसर क्या आया? अगर एम्पियर में आया है तो इसको 200 किलो ओम कर दो। कैलकुलेशन तुम करके बताओगे ना कितना आ रहा है, एम्पियर में आ रहा है मिली एम्पियर में आ रहा है तुम्हारा। वोल्ट डिवाइड बाय ओम क्या आता है, एम्पियर आता है मिली एम्पियर आता है। Now just you are not able to tell me 4.3. Okay, audio is not available. Audio is available or not?
Sir,
No,
you are
sir.
audible.
Sir,
Perfect, sir.
audible.
Why people are saying audio is not available? Okay, so now this is a milliampere is fine now. Parampreet,
Sir, that IB was in milliampere.
no, see you're not understanding. Okay, why are you confusing me? Okay, I'm asking
Sir,
what is
200 ohm, 200 ohms, sir.
if IB is this one, this was about 5 minus 0.7 upon 200. Okay, so this is if it's 200, what is coming? It's the current is coming in ampere or milliampere.
It's a milliampere, 0.21.
You sure? This is 4.3. Okay, 4.3 divided by 200. Okay, so this will come in ampere. How it come milliampere? That's why I'm telling this resistance. This is not 200. This is kilo ohm.
Okay, then that I made news.
Okay.
Okay.
Yes.
Is it 200 ohm?
Now this is 200 ohms, right? So you divide this from 0.0.015. That will be in ampere. So I'm taking resistance here. Okay. So that will be milliampere. Now I've corrected the resistance. Okay. Now this is your minus 10, 3 kilo ohm. Okay, and then this is a plus VCE. Okay, and then it's equals to 0. So now what is the, now put the value of IC and tell me what is VCE. What is the VCE? Tell me. 10 minus IC is 2.15 milliampere into 3. Okay, 10 minus this cancel, so this become how much? 3.45. How much is coming now? 10 minus 3.45, 6.45. How much coming?
0.55.
6.55.
ओके, ये कैलकुलेशन ठीक है, पहले बताओ। ये 6 ये आएगा 6.45. ओके, तो आंसर क्या आएगा आपका? आंसर आएगा आपका 3.55 वोल्ट. ओके, दिस इज योर VCE. ओके, so now you have VCE also, you have IC also. Okay, now tell me what is VCB now. So VC is well above your, it's not visible now. So this is visible now. Okay, let me raise up the scale. Okay, so okay, this will be now 10 minus 6.45, that is 3.55 volt. Okay, now this value is well above your 1. That means obviously this VC is positive. So which a VC greater than 1, your operation region is automatically active region, because this is a forward, this is IB is flowing in the circuit. So that is, this is a forward bias. I with 5 volt battery, this forward bias, okay, is greater than 0.7. So it is forward bias, and VCE is making this junction, this forward bias. Now if you want, you can find the VCB value. What is the VCB value? So your VCE equals to VCB plus VBE. Okay, now if you want to find what is the VCB, that would be VCE. VCE is 3.55. 3.55 minus VB is 0.7. Okay, so what is coming VCB? Tell me what is the value of VCB? कितना आ रहा है VCB का वैल्यू? कितना आ रहा है बताओ?
2.85.
2.85. Sure. Okay, I'm writing here. So VCB is now positive. So VCB is positive. That means your junction is reverse bias. Okay, that confirms the reverse bias. Okay, and IB, VB, this voltage confirms that is the forward. This is the junction is forward bias. This is making forward bias, and this is making you a reverse bias. And the operation region is active. Okay, the operation region is active. Okay, now what is operating point? Okay, operating point. Now this is your graph. IC and VCE. Okay. Now if I call this is VCC, so I can write this is VCC. Now these are your curves. If I plot different voltages and if I plot the current changing, this type of curve will get. Okay, you get this type of curve. Now this is the minus VCC. If I call this RC, that will give you ICRC. Okay, and that will give you VCE equals to 0. So your VCE, okay, VCE will be your VCC minus ICRC. Okay, and this is the equation of line. Okay, VCE versus IC curve. Okay, this is the equation of line. So if I plot this one, this has a negative slope. Okay, so this will go like this. And if you are
Sir, what you write that formula VCE equal to?
VCC minus ICRC. Okay, VCE is equal to, this is the VCC, J voltage, how much is voltage, how much is getting drop here, remaining coming here. So VCC minus, so VCC minus ICRC will give you VCE, VCC and drop here, remaining coming VCE here. Okay, and this is the equation of line. Okay, now if I put here VCE equals to 0, then IC will be what? IC will be your VCC upon VC 0. If VC is 0, if VC is 0, then IC will be your VCC upon RC. Okay, and this current is called IC saturation. This current is called IC saturation. Okay, and this point is your IC saturation. Okay, similarly, if your VCE equals to VCC, okay, then what will happen? Your IC will become 0. If VCE equals to VCC, okay, then what will happen? Your IC will become 0. So these two, okay, these are the 2 points and end points, okay, and this is your, this point is called VCC and 0, and this point is called your 0 and IC saturation. Okay, so if you want to find the IC saturation, you just need to put VCE 0 here, that will give you IC saturation. Okay, and this line is called load line. This line is called load line. Okay, now we have solved the circuit and we have calculated the value of VC and IC. Okay, so what is the value of VC? Tell me, what is the VC value? 3.55 volt. 3.55 volt VC. Okay, so VC is 3.55, and what is the current IC? We have calculated 2.15 milliampere. Yes or no? Okay, so this point VC versus IC is called your operating point. Okay, so this is called your operating point. So in question they're asking calculate the operating point VC IC, and they're asking what is the operation region. So operation region is active because VCB is positive. Okay, now I will tell you the simple method to find whether a transistor is an active region or not. Okay, so for that, what you need to supposed to do, you need to compare your IC in the circuit with IC saturation. Okay, if IC is less than IC saturation, then you can say that my operation region is active. And if your IC is greater than your IC saturation, then you can say the operation region is saturation.
There is an active region. 3.33 milliampere is comes. IC saturation.
IC value कितनी आई थी? 3.
IC value was 2.15 and IC
Yes,
ISAT is 3.33.
Yes, that's what the same thing I'm telling. So now in this question, what we calculated IC was about 2.15 milliampere. Okay, and the same circuit, if I calculate the IC saturation, okay, so IC saturation will be कितना आएगा? IC saturation will be your VCC upon RC, the 10 upon 3 kilo ohm. Okay, that is 3.33 milliampere. That means my IC is less than IC saturation. So you can call it this is active region. Okay. In some question, if IC coming greater than IC saturation, then you call it just that is a saturation region. Okay. And that is the operation region is saturation. Okay. So if you have doubt, please ask. If this point is not clear, let me explain once more. Okay. Because it's very important. Tell me, is it clear or not? Parampreet,
Clear, sir.
Radhika.
Yes, sir. Clear.
Okay, so you need to calculate what IC and IC saturation and compare. Okay, so automatically you know if you get VC close to 0, then you should have doubt. Okay, if VC close to 0, automatically that is going in saturation, or VC negative, then also it is going negative. Okay, if the graph is going, VC is going here, VC become negative, matlab minus connected with an N. That is your saturation region. This side, this is saturation region. Okay, so you have to see the values of voltages. Okay, and then accordingly you have to doubt, and then you exactly calculate and find out whether the operation region is active, saturation, or cutoff. Okay, for cutoff your IC should be 0, so the IV will be 0. Okay, so it should be near to 0. Okay, now let us solve one more problem. This came in your net and JRF June 2015. June 2015. Okay, so they are giving you 10.7 volt. This is your 10 kilo ohm. Okay, this is your transistor. This is your 10 volt. Okay, and here this connected IE. This is your IE. Okay, current is coming here, and this is your 2 kilo ohm. Okay, and current is coming like this. Okay, so this is your IC, IE, and now this here, this is your IB. Okay, find out, tell me, and calculate and find out what's happening in the circuit. First, calculate IB. Beta, take 100. Okay, take beta equals to 100.
IB equal to 1.
IB equals to 1 milliampere. Good. बाकी लोग calculate करो. So all of the student, please calculate. Don't say it like this only. Okay. If you don't calculate, you will not understand. So IB is 1 milliampere. Okay. So this is your minus VB. You take 0.7. So minus 10.7. Okay. I'm writing input. Then IB into RB, that is 10 kilo ohm. Then plus VB 0.7 equals to 0. So your IB becomes 10.7 minus 0.7 divided by 10 into 10 raised to power 3. Okay, so this gives you 10 upon 10 into 10 raised to power 3. Cancel out. So this gives you 1 milliampere. This is 1 milliampere. So IC will be what? IC will be your beta IB, and beta value is 100. Beta IB. So 100 into 1 milliampere. Okay, कितना आ गया? 100 milliampere. 100 milliampere. It's too much. Okay. Now calculate IC saturation. How much coming? IC saturation. Bulela, if I want to calculate IC saturation, what should I do? If I want to calculate IC saturation, what should I do?
In reverse bias.
I'm asking IC saturation. What is how to calculate IC saturation?
Its value is 10 by
Huh?
10 upon
Uh,
2
10 upon,
into
very good. 10 upon 2 into 10 raised to power
minus 10 is to power 3, sir.
10 raised to power 3 kilo ohm. Why you
Yes,
getting? Okay, because
3.
PCC upon RC. Okay, this is your IC saturation. How much coming? 5 milliampere. 5 milliampere. Okay, and this is what? 100 milliampere. That means your IC is less than IC saturation. That means this circuit is not in saturation. Okay, so whenever circuit comes in saturation, then
Sir,
what?
less.
Huh.
Its value is less than means active region, sir.
Here IC saturation should be, means IC saturation should be now what is there? IC saturation greater than IC saturation is, sorry, IC saturation is less. IC is greater than IC saturation. Okay,
Then saturation
so this
region.
is saturation. Okay, because current become higher than IC saturation. Okay, now whenever you put IC saturation, okay, now your current is IC. Now if you try to solve, if you look your graph, okay, whenever you are in saturation, you are here and this is here. Okay, so whenever IC gets saturated, your VC is 0, automatically 0. Your VC, if you put the IC value here, now use this IC value and calculate VCE, that will come negative. First calculate how much is coming. What is the VCE value? Tell me in the circuit. What is the VCE value? What's the value of VCE? If you put
minus 196 volt.
yes, something come minus, okay, but this curve cannot go minus because you're putting plus here. Okay, this curve cannot go in my VC cannot go minus. Okay, that means this value is not correct what we're using IC. Okay, because the current cannot increase greater than IC saturation. This we have seen the load line. These are limits. Current cannot increase IC saturation. So when you calculate now VCE, then you have to put VCE. You have to put IC equal to IC saturation. Okay. So if you put IC equal to IC saturation, automatically VC comes 0. Now what is the VCC minus IC saturation? You have to use IC saturation here. IC saturation RC. Okay. And this is 10. 10 minus, this is how much? 100 milliampere. VCC is 10 and IC saturation is 100 milliampere. Okay. And what is RC? Why RC is 2? IC saturation is 5 milliampere.
Saturation 5 milliampere.
5 milliampere. And then 2 kilo ohm. Okay. So 2 kilo ohm plus this cancel, this 10. So it becomes 0. So your VC becomes 0. So now your operating point. So your operating point is now 0. Okay. And IC saturation 5 milliampere. So this is your operating point now. Okay. So don't put the value negative VC. Okay. And once this is a 0, VC is 0, automatically VCB also negative. Okay. Or you take this VC negative value, whatever you calculated, automatically VC becomes negative. So VC becomes negative. That means it is also forward bias. Okay. Are you getting my point? VCB becomes negative. Then this junction becomes NP. This becomes forward bias. So forward bias become your saturation region. Okay. Now, just let me modify this question a little bit. Okay. Now I'm taking beta equals to say 10. Beta equals to 10. And I'm changing the voltage also 5. I'm making it 5. Okay. Now find tell me operation. What is the operation region? And tell me operating point also now. Now IB will be what? IB will be your 5 minus 0.7, 5 minus 0.7 upon 10 kilo ohm. That is 4.3. Okay, 10 into 10 to the power 3. That become 0.43 milliampere. 0.43 milliampere. And if I calculate IC, that is beta IB. Okay. Okay. So beta is what? Beta is 10. IB is your 0.43. Okay. Milliampere. So this become 4.3 milliampere. Okay. This is IC 4.3 milliampere. Okay. Now find out the IC saturation. Okay. Okay. That will be 5 milliampere. Okay. So obviously your IC is now less than IC saturation. So operating region is your active. And you can find this calculating by VC also or VCP also. Okay. So operation region is your active. And what is the operating point? Tell me, what is the operating point? What is the operating point? So in order to find the operating point VCE, okay, you need to calculate equation VCC minus VCC plus IC RC.
1.4 volt and 4.3 milliamp.
Okay. So ICRC plus VCE equals to 0. So VCE will be VCC 10 minus ICRC. Okay. And IC value कितनी आई थी हमारी 4.3 milliampere into RC is 2 kilo ohm. Okay.
Sir, IC saturation na sir.
Why?
Its value is 5 milliamperes.
So why I will use IC saturation when it is active region? I will use the real IC value. If it is okay, if it is saturation, then I will use IC saturation. Okay.
Yes, sir. Yes, sir.
So this will be your 8.6.
So please repeat last statement, sir. A 4.3. Why we took that one?
See, if you are in active region, then you have to use the current whatever you're using IC, you're in active region. Your current is not saturation. Your current is less than IC saturation. You are not reached to saturation. So why are you using IC saturation? IC saturation you use when you are in the saturation region.
Okay, okay, sir.
Okay.
Get.
So now,
Got it.
so now this is your real current. Okay. If this goes above IC saturation, then you have to take IC saturation because current cannot go greater than IC saturation. Okay. So how much coming? This is 2 point. How much? 2 point or 1.4? 1.4. How much coming? Some,
1.4.
some calculation mistake is there. 10. Just why I have a different values. Okay. So VC is your VCC 10 minus 4.3. Okay, 2 kilo. I have kept on 2 kilo. Okay. Okay. So this will become your 1.4 volt. Okay. Fine. Okay. So this is your operating point. So 1.4 and IC is your 4.3 milliampere. This is volt. And this is your operating point Q. Okay. So I have done at least 3 problems. Now at least you should understand that how to find operation region. Okay. Now the next topic is your biasing. Okay. So let us discuss what is biasing. Okay. So biasing, what we are doing here, this is basically biasing. Na? I'm applying 2 batteries here. I'm giving biasing here. I'm giving biasing here. Okay. So each transistor, at least 2 voltages are required. At least 2 biasing are required. Okay. So, but this type of biasing, okay, is not cannot be used for making devices. Okay, because this become too costly, na? Because if I have a 1000 transistor in the chip, okay, And if I started giving all the transistor 2 volts, 2 batteries, the cost will very increase very high. Okay, so this is not a cost efficient way of making the biasing. Okay, so generally if you have a 100 transistor or 1000 transistor, whatever transistor, all transistors given the biasing with a single battery. Okay, so now what I'm giving here 5 volt here, I'm giving 10 volt here. This all can be done with single battery. Okay, this is the first thing. Okay, because this is not a cost effective way. Okay, so we have to change other way. Okay, and then what happens that your beta, this beta is temperature dependent. So as temperature increases, this beta varies. So this beta varies. IC depends on beta. Your IC also changes. So IC changes means your operating point also shifting. Okay, so you want to reduce the cost, and cost से भी ज़्यादा important point है application point of view से you don't want that your operating point should be destable. Your operating point should not move in the graph, because you want to keep always in active region or whatever application. If you want to do amplify, you want to keep it in active region. If you want to do a switch, you want to keep it a saturation region, or if you want to put it cutoff region. But if temperature is changing, okay, then beta is changing. Beta is changing, then you are automatically IC changing. IC changing means that your operating point is varying. So biasing is required. Okay, so the main purpose of biasing. Okay, so I need a biasing which make this point suitable. My operating point should not vary. So what are the purpose of biasing? Okay, so biasing, transistor biasing, okay, or BJT biasing. You are discussing here BJT biasing. Okay, BJT biasing. So what is the purpose of biasing? Number one, first of all, where I want to fix my point. Okay, so to fix the operating point, to fix the operating point. Okay, the second is to stabilize the operating point, to stabilize the operating point. Okay, and the third point is, okay, third point is that your biasing, okay, your biasing should be such that it should reduce the cost. Okay, so what I can write, I can tell that cost effective. Okay, so the third point is your batteries are costly. Okay, so batteries are costly. Okay, so and the maintenance is very high. Maintenance is high. Okay, when I say stabilize the operating point, that means we have to find a biasing, okay, which is beta independent. That means my IC should be, when I say stabilize, that means stabilize means this IC should be independent of temperature. Okay, IC should be independent of temperature, or IC should be independent of your beta. Okay, so I need a biasing which makes my current independent of beta. Okay, that is our purpose. Okay, so let me give you this in detail. Okay, so what happens when you increase the temperature? Okay, what happens when you increase the temperature? So when you increase the temperature, okay, or say T increase, it increases the beta. Okay, and when say this like this, okay, and when beta increases, automatically your IC increases. Okay, so your IC also, what I'm doing is beta. Okay, beta, and this is your IC. So your IC also increases. IC increases. Okay, now when IC, or main thing is before beta, the reverse saturation current ICO. Okay, we have seen when we're discussing transistor, your reverse saturation current is dependent on temperature. Okay, reverse saturation current. Okay, increases with increase in temperature, with increase in temperature. Okay, so when you're increasing the temperature, you are increasing the beta, or you can say you can also increasing the ICO, reverse saturation current, ICO. Okay, and when beta increases, your IC increases. Okay, so your IC increases. When ICO increases, then also your IC increases. Okay, so that dependence we have to reduce. Okay, and one more thing, when I increase the temperature, what happens? When I had discussed the IV characteristics of diode, I told that VBE decreases. Yes or no? When I increase the temperature, my VB is also decreases. Okay, and the decrease in VBE also result in increase in IC. Okay, so that those things, now everything I need to control. Okay, so that for that you need the biasing. Okay, now tomorrow we'll discuss different type of biasing. Okay, how can I give the forward bias to the input junction and reverse bias to reverse bias to the output junction using single battery. Okay, and we'll see how those biasings, okay, in order wise. Okay, how we'll start with the elementary biasing, and then we'll reach a circuit, okay, which is beta independent. Okay, so thank you. I'm stopping here. Any question, tell me. Audio is not available. Raj Kishore is saying
Yes, sir.
audio is not available.
ऑडियो इज अवेलेबल सर, आ रहा है.
बोल रहे अवेलेबल नहीं है.
आ
ओके
रहा है सर अब.
ओके ओके ओके. सो आप बोलो, कोई क्वेश्चन हो तो पूछो. Ask me if there's any question. Otherwise, I'll discuss the biasing tomorrow. Okay. ये मैंने डिस्कस किया था क्या? टेम्परेचर इफेक्ट ऑन IV characteristics of diode. Did I
नहीं
discuss
सर,
टेम्परेचर इफेक्ट ऑन डायोड?
टेम्परेचर इफेक्ट नहीं करा. नहीं सर,
नहीं करा ना, तो वो भी करा देंगे. चलो ठीक है. तो अभी तो ये देखो कि आपके जो IC टेम्परेचर बढ़ता है तो आपका रिवर्स सैचुरेशन करंट बढ़ता है. ओके, और रिवर्स सैचुरेशन करंट बढ़ेगा तो आपका IC बढ़ेगा ही, क्योंकि IC इज इक्वल टू IC में आपका IC सैचुरेशन ऐड होता ही है ना. IC क्या है? IC होता है आपका बीटा अल्फा आई, जैसे कॉमन बेस है तो अल्फा आई प्लस IC सैचुरेशन. सिमिलरली अगर NPN ट्रांजिस्टर लें, ओके, just now we have seen common emitter configuration. We discuss. If I take common emitter configuration, okay, common emitter configuration, तो इसमें हमने क्या देखा था कि हमारा जो कॉमन बेस में हमारा जो मेन इक्वेशन था IC का, दैट वाज व्हाट, अल्फा IE. ओके, और अल्फा IE और क्या था, ICBO था. ओके, और हमने देखा था कि जो IE है, I बेसिकली योर IC प्लस IB plus ICBO. Okay, now if I send this here, if I take IC 1 minus alpha, okay, that will give you me alpha IB, okay, plus ICBO. Now if I send this IC here, this becomes alpha upon 1 minus alpha IB ICBO upon 1 minus alpha. Okay, so this is the current equation for common emitter configuration, and this is your beta. This is your beta IB, and this is your reverse saturation current ICO. Okay, this is your reverse saturation current ICO. So this is the equation for common emitter configuration. Okay, so current depends on beta and reverse saturation current. So when increase the temperature, this current increases, this beta increases, automatically IC increases. Okay, so we need to control this IC by biasing. So tomorrow we'll discuss this one.
Thank you, sir.
Okay, thank you, sir.
Sir,
हाँ
सर हमें एनालॉग के लिए कौन सी बुक फॉलो करनी चाहिए?
कौन बोल रहा है?
सर माई सेल्फ अंजना।
हाँ अंजना, अभी तक कौन सी बुक फॉलो कर रहे हो आप? अभी अभी तक क्या कर रहे हो?
सर
अभी
अभी
हाँ, अभी कौन सा बुक पढ़ रहे हो तुम बताओ?
सर अभी तक तो कोई नहीं।
तो उसके लिए हाँ, एक तो बॉल स्टेट की बुक है जो ड्राइव में पड़ी हुई है। ओके, बॉल स्टेट की बुक है, वो पढ़ो इलेक्ट्रॉनिक्स के लिए। और एक बुक है चट्टोपाध्याय करके है, वो भी अच्छी बुक है। तो बेसिकली अगर आपको ट्रांजिस्टर पढ़ना है, ट्रांजिस्टर के लिए बेस्ट बुक है आपकी बॉल स्टेट। ओके, बॉल स्टेट और जो हमारा स्टडी मटेरियल है उसको आपको फॉलो करना है। जो प्रवेगा का स्टडी मटेरियल है उसको फॉलो करना है ट्रांजिस्टर के लिए। सर्किट के लिए मैंने एक बुक ऑलरेडी आपको भेजी थी, फंडामेंटल ऑफ इलेक्ट्रिक सर्किट। ओके,
यस सर।
दैट बुक यू टू फॉलो। ओके, और डायोड के लिए जो क्लास मटेरियल है और जो मेरी क्लास नोट्स है दैट इज सफिशिएंट। उसमें मैंने बहुत सी प्रॉब्लम ऑलरेडी करा दी आपको, वो सफिशिएंट है। ओके, and
थैंक यू सर।
when we'll discuss OPM, I will tell you what to follow. Okay. Okay.
Thank you, sir.
Thank you.